OK. So now we've seen how computers can represent numbers. But usually when we're working with a computer, we represent much more than numbers, right? We want to start representing the letters we type on our keyboard. Remember, the computer is still fundamentally zeros and ones. So what we need to do is figure out a way to translate from these zeros and ones into something that we can actually represent that is actually helpful to represent, like a letter. So I have here, to introduce this, a clip from the movie Wanted. So this is 2008 with Morgan Freeman explaining binary.
But to deliver. Every culture in history has a secret code, one you won't find in traditional texts. 1,000 years ago, a clan of weavers discovered a mystical language hidden in the fabric. They called themselves the Fraternity.
I'll be honest with you, all I see are threads.
Come here.
Look there. You see that one thread that missed the weave and lies on top of the others?
Like a mistake?
No, it's a code.
If the vertical thread is on top, it's a 1. If it's below, it's a 0.
Binary code? What does it say?
It's a name, a target.
So unfortunately, our binary will not be as dramatic as that. But what just happened here is Morgan Freeman, who can, if he cannot explain binary, then I don't know who can, was looking at a series of bits. So some of those bits were 1s, and some of them were 0s. And suddenly from that, he got some name. And that name happened to be this next assassination target, which we definitely won't be doing here. So from those 0s and 1s, he got that name. So to do that, that means he had to have some kind of encoding, some way of going from 0s and 1s to a name. So we encounter some encodings pretty frequently. So if you've ever been on a ship, you might have seen something like this. So this is one encoding that we have that maps something to characters. So here we have a series of flags, and each of these flags represents a different letter. So if a ship wants to communicate some message, it can't simply send letters over to another ship, because that just doesn't make sense. So instead, it needs to have some way of encoding its message using something it can send. So the ship does have flags, so the ship can use flags to start sending a message. So here, whenever we see, for example, this flag with the yellow cross, we know that that's going to represent the letter R. So we've encoded that letter R as this flag. So another type of encoding you might have seen before is this. So this is Morse code. So in order to send, for example, the letter Z, I want to send some pattern of sounds that looks like this. And now we have someone on the other end who's going to hear these pattern of sounds, and they're going to have to know how to translate that to a letter. So that means that we've created some mapping, some encoding that maps this sound pattern to an actual letter. So in computers, we're actually going to take the same exact approach. While we're not going to use flags or sounds, else that would be annoying and probably take up a lot of space, we're going to use something called Ascii. So Ascii is a character encoding that defines encodings for 128 different characters. So for example, if I want to encode the letter capital A in Ascii, a computer doesn't know what a capital A is. But we've seen that a computer does know how to represent numbers, because we can simply use that binary sequence of 0s and 1s. So to represent the letter A, I can instead say, whenever I see the number 65, that's going to refer to an A, or a capital A to be specific. So that means that if I want to represent an A, I'm just going to use the number 65 everywhere. My computer has this mapping from numbers to letters that's shared across all different computers. They all know that this 65 corresponds to a capital A. So in the same way, the number 97 was chosen to represent the letter lowercase a. So whenever we see a number 97, we're actually referring instead to a lowercase a. So here is a large mapping of the Ascii encoding. So this is called the Ascii table. We can see here that in the red is the character that we'd like to encode. And then all the way over to the left is the decimal representation of that number. So W, for capital W, for example, we can see is an 87. So there's no need to commit this to memory, because I certainly haven't. But this is the most basic of mappings between some characters and some numbers, which really are just sequences of bits. So let's look at an example. So let's say I'm a computer, and I want to represent this text, CS space E-1. So to do that, I need to figure out what the ASCII code for each of these letters is. I want to take some letter and turn it into a number using this same mapping that everybody knows. So by going back and forth on that ASCII table, I figured out that CS space E-1 is represented by this series of numbers. So now, if I'm a computer, I still don't know what the digit 6 is. I can only work in binary. So really, in order to represent this message, the computer will do something like this. So this first value here is a 67, and the second value is whatever the ASCII code for S, capital S, happened to be. But now, suddenly we're representing text using only zeros and ones. So this is nice, but we said that ASCII only defines something like 128 different characters. That's actually pretty limited compared to the number of characters on your keyboard. So we have other encodings as well that kind of build on top of ASCII. So one of these is called UTF-8. You may have heard this on a web page, or if you've ever downloaded a Word file and got some weird error message. But what UTF-8 does is it allows us to define additional characters that aren't simply letters. So one of my favorite Unicode characters is this, which is a snowman. So this is not actually just a picture of a snowman. This is actually the Unicode character snowman. And if you go to a site, Unicode snowman for you, you can see here that this, now I'm in a web browser, and this is actually a character that if I take my mouse and I highlight it, I can copy and paste a snowman into my address bar. Because this isn't an image. This is actually a character that's represented now with UTF-8, which is just, rather than this ASCII table that could fit on the slide, is this huge table of really anything you might ever want to represent. So another one of those characters that is represented in Unicode but not ASCII is this, which is called the Unicode Love Hotel. It's actually, someone took the time to not only draw this, but to put it into the Unicode standard, so that if you ever needed to type a Unicode Love Hotel, you can do so without having to resort to an image. So if you go to, for example, unicodelovehotel.com, you will get just this character in case you ever need to use it. But the point of this really is that ASCII isn't enough, right? I mean, so not only do we need to represent snowmen and hotels, but we might also want to represent something like accented characters, or the pound sign, or anything else that's not simply a letter. So it's actually somewhat necessary in that sense, in that just typing letters on a keyboard probably isn't enough to express everything we want. And UTF-8, the goal of this is to really take everything ever we could possibly want to type and represent it somehow, still using only zeros and ones. Suddenly, though, we just have this small mapping of numbers to characters. We have this huge mapping of really big numbers to kind of silly characters. So any questions there? Yeah?
How does ASCII distinguish real number between 67 and the digital 67? The number 67.
Yeah, so that's a great question. So ASCII, we saw, it defines numbers. So let's flip back to our ASCII table. So we said that we want to make what if we wanted to represent the number 67 in ASCII? So if we look at our ASCII table, it looks like the number 6 is actually represented by the ASCII code 54. And so that's how your computer ensures that it's not confusing. When your computer is given some block of data, we have to tell that computer what this block of data is encoded as. So if we have this string, we tell our computer this is an ASCII string, suddenly it knows that all of the data that inside of that message is actually ASCII, and it's no longer actual characters. So by specifying what encoding we want to use, which is something that your computer is just going to do transparently and not to your knowledge, that's how we can start to jump from the number 67, for example, to the ASCII code for capital C. Other questions on character encodings? So if you actually visit a website, and as we'll do soon, we can look at the source code of that website, or the code that was written in order to create the website. Really frequently at the top, we'll see something like encoding equals UTF-8. And that is one way that your computer is guaranteed to know which of these encodings to use. Luckily, UTF-8 is actually built on top of ASCII. So the ASCII representation for A and the Unicode representation for A are the same, which worked out really nicely so we can minimize confusion among people and computers. OK, so storing data as zeros and ones is nice, but suddenly, if we have some really big numbers, and suddenly we have 2 or 4 gigabytes of data, which is a lot, we don't really want to know how many bits it is, because it's going to turn out that it's a whole lot of bits to store something like a music file. So instead, we start to refer to these in larger and larger quantities. So our smallest quantity that we talked about was a bit. And the bit was either a 0 or a 1. If we take 8 bits now, a sequence of 8 bits that are all part of the same representation of data, we're going to call that sequence of 8 bits a single byte. So by the way, if you take 4 bits instead of 8, it's not a byte, it's a nibble. That is actually the technical term, albeit clever. So now suddenly we have 8 bits, and that's equal to 1 byte. So that's still a really, really small amount of information. In fact, that's still on the order of a single ASCII character. So now if we want to represent more than a byte, we can start adding these prefixes. So a kilobyte, for example, is equal to 1,000 bytes. A megabyte is 1,000 kilobytes. A gigabyte, as you might expect, is 1,000 megabytes, and so on and so forth. So when we say your computer has between 2 and 4 gigabytes of RAM, that means we actually have a whole lot of bits, because we're multiplying each of these steps by 1,000. So your hard drive, on the other hand, which has between several hundred gigabytes and maybe several terabytes, that is even more bits. But to say that your hard drive has 11 billion bits isn't really that helpful, so we want to compress that down into terabytes. So any questions? OK. So before we finish up, I want to introduce something that we'll be covering a little bit later in the course, and that is thinking like a computer. And a computer is going to solve problems very methodically. And it's also going to solve problems maybe in a different way than you might expect. So if I ask you a question like this, what chair is everyone sitting in? So to answer this question, everyone might take the time and say, I want to look to my left, and I'm going to count 1, 2, 3, 4, 5, the number of chairs that is to my left. So that's nice, and it's going to eventually give ourselves the right answer. But it's not very efficient, right? Suddenly we have all of these different people, each separately taking the time to count left, 1, 2, 3, 4, 5. And we can speed this up a little bit. We can count by 2s. We can say 2, 4, 6, 8. But still, we have everyone in a room doing the same exact thing to get some correct answer. So I'm going to propose a different way to solve this problem. So rather than everyone independently counting where they sit, we're going to do something like this. So each person can say, I want to look to the person to my left, and I want to ask, what seat are you sitting in? So now, if there is no one to your left, I'm going to say 1. The next step is to say, I want to add 1 to the answer of the person to my left and say it out loud. So let's see what happens when we run this. So in our front row here, we have Ben, RJ, and Lexi. And so if you guys would like to execute this computer program, what happens? So we'll start with Ben, and we'll move that way.
1, 2, 3.
OK, that was close, though we didn't actually follow the program. So the goal, so if you're a computer, remember, we need to actually execute every step in order. So even though it might be a little pedantic, we need to actually take the time and execute every step. So if we want to start, OK.
Do I need to ask all the way over to there?
So we'll just stay there, but make sure we actually, rather than just saying 1, we need to actually ask. So this is to your right, sorry. So to your right now, you want to, OK. So you want to ask all the way to your right and see what happens. So now let's try again. If Ben starts.
Where are you sitting? Where are you sitting? Where are you sitting? 1, 2, 3.
So there we go. So this was a little bit different. Suddenly, not all 3 of them were counting the chairs to their left. Instead, each person did one small step. They said, I'm going to simply ask the person to my left. And so when I've done that, I've taken this larger problem. I need to count this really large quantity, and I've broken it down into a smaller problem. Rather than counting all these chairs, I'm just going to ask a simple question. So now suddenly, if everyone starts to do this, this problem gets progressively smaller and smaller and smaller. Right? In fact, it gets 1 chair smaller with every direction we go to the left. until at the end, this last person can come up with an answer for themselves. And now, once this one person has an answer, we can start to propagate that back to the original person. And so in computer science, we call this recursion. And so in the process of recursion, we take a big problem, like the problem we just had, and we break it up into somehow a smaller problem. And now you'll notice that I didn't have separate instructions for Ben and RJ. Ben and RJ actually followed the exact same set of instructions. Yet, when they executed them, it turned out a little bit differently. Right? Somehow Ben got the answer 3, and RJ got the answer 2. So I didn't need to tell them anything different, but I saved them a lot of time. So it turns out that if we had all counted individually, that problem would have looked something like a quadratic, so a curve that goes really kind of skyrockets up. Where now if we do this instead, each person, rather than counting 1, 2, 3, 4, 5, suddenly it looks more like a line, which is much, much more efficient. And so this is just one way of taking some problem and thinking about it not only very formally, but also in a more efficient way, and something you might not expect. And so when later we write computer programs, we can feed them things like this very specific set of instructions that, unlike Ben and RJ, will listen to them, that when you formalize them very nicely, we can start to get answers that are much more efficient than trying to do things ourselves. So any last questions? Yeah?
Actually, what I was curious about in terms of what you were saying in terms of binary. Now, binary is basically the language that computers use to create instructions, or I'm just curious.
Sure. So what do we mean when we say binary?
Binary and also ASCII to.
Yeah. So also ASCII. So the best way to describe binary is how we represent data. So if we have some quantity like the number 20, we can represent that in a number of ways. I could give you 2 dimes and say that's 20. I could also write down the number digit 2 followed by the digit 0, and I can say that's 20. So another way of representing 20 might be the binary representation, which is just some way to interpret the quantity 20. So ASCII is a little bit different. It's kind of a layer on top of that. So ASCII also is a representation of data. So somehow when I give you the letter A, I want to represent that somehow. And I can represent that with the Ascii encoding of that letter. So ASCII kind of builds on top of binary and uses binary in order to express things that aren't simply numbers or zeros and ones. Other questions? Yeah?
I was going to ask, why is binary used for computers? I think based on that answer, it's just simply efficiency. Is that the idea?
Sure. So the question is why is binary used in computers? So back when we were talking about how the computer turned on, we had all of these different electrical components, and they're all connected via these circuits. And so as far as the electrical components are concerned, it's really easy to represent on or off. So whether there is electricity flowing through something, or whether electricity is not flowing through something, or whether a light is on or whether a light is off. So at the really low-level electrical component level, that's how we can represent either a 0 or a 1 in actual physical hardware. So because that's how the hardware works, the hardware can either do a 0 or a 1 with this light or electricity. That's when we just say, OK, well, given this limitation of our hardware, that we can use a 0 or a 1, let's start to build on top of that in order to somehow get from that really low-level kind of meaningless distinction to suddenly the things that power cat videos.